Yeah, thank you very much. Thank you very much for the invitation, and it's a very interesting conference. And as you have heard already in the previous talks, there is a growing interest in applications of data estimation and parameter estimation and data assimilation methods in life sciences. In my talk, I want to discuss aspects of using these methods in future in the field of cardiac dynamics. And I want to first give a short overview of the talk. First, I want to say a few words about features of cardiac dynamics. When you look at it from a physics or dynamical systems point of view, it's an excitable system with some particular features. Then I will present you an overview of the measurement modalities which are available to study cardiac dynamics. We will say a few words about mathematical models that can be applied to model these systems. And then I will show you some example of an application of these models for studying novel methods for defibrillation as an application also of the whole machinery we want to develop. I will then continue with a list of parameter estimation talks to be solved in the future in this field. And I will, at the end of the talk, say a few words about some preliminary work we used synchronization methods for estimating parameters and state variables. And we also came across the problem of estimating variables, and this estimability problem will be addressed at the end using delay coordinates maps. Okay, so if you go to a medical doctor, he or she may take an ECG of you to find out whether your health is in good condition or not. And if everything is okay, you will see a pattern like this. This is a normal heart rhythm. But this trace was from a patient in a hospital where suddenly a transition took place to a different signal that you can see here. It looks a little bit like a sinusoidal. It has a higher frequency, and this is what the medical doctors call tachycardia. And then there's another transition here to a pattern which is even more irregular, and this is fibrillation. So what is underlying these patterns that you see in the ECG? It's excitation wave, electrical and mechanical excitation waves on the heart. So in the first case, in the normal heartbeat, you have basically a plane wave starting from the apex triggered by the sine node, and this leads to the contraction of the heart. So this is fine. But then there may be spiral waves occurring, which are typical features of excitable media. That's why I want to say a few words about this type of dynamical systems. And the rotation frequency of these spiral waves is what you see here as a higher frequency in the tachycardia case. But then things may become even worse, and these spiral waves may become unstable, and you end up in a state of spatial temporal chaos. And in this case, you see this fibrillation. And this is a very dangerous case because now the heart is not coherently pumping anymore. There is no oxygen supplied to your brain, and after a few minutes, you would be dead if you don't take any countermeasures like defibrillation. I will come back to that later. So the heart is, or the heart tissue is an excitable medium, and excitable systems have a particular feature. They are stable at a fixed point, and if you perturb them weakly below some threshold, basically nothing happens. They return immediately to the fixed point, and you have only a very weak output. But if you exceed your perturbation above threshold, then there is a kind of an excursion in state space, and you will see that the system produces a strong output peak, like an action potential, for example. You can do this with a stronger stimulus that has no big difference. And you also can, of course, apply another pulse, and you get another response. But if you do it too early, so that the system is still running around in state space and have not yet returned to the stable fixed point, then you will only see a very weak perturbation or output pulse here due to the second perturbation. And this period where the system needs to recover is called the refractory phase. And this is an important feature of all excitable systems. So here is a very simple mathematical model, generic system, the so-called Berkeley model, consisting of two variables, u and v. These equations, or this part of the equation, describes the local dynamics, and then there is a diffusion term to couple many of these excitable systems in a sense. And you see here the threshold value for the variable u. If you exceed this value, then you will have an excitation. So if we solve this differential equation, and if we perturb it, for example, here in the middle, you see these concentric waves. Here is a snapshot, and the area in blue, in bright blue here is the area which is at that moment in the refractory phase. So you cannot stimulate another pulse here. You have to wait a little bit until this has moved further away, and then you could stimulate again. So this feature leads to the existence of refractory phases and regions, leads to the fact that you very often find so-called spiral waves in these media, as you can see here, and they are rotating, and they may even rotate on a larger circle here, the spiral tip, or it may follow a more complicated path, like the one on the right-hand side. You can do this also in 3D. Then you will find so-called scroll waves, and you could also modify the system, in particular this one, to obtain spatial temporal chaos. You only have to raise here the u to the power of 3. Then you get spatial temporal chaos. We studied many systems with spatial temporal chaos recently, and we found out that most excitable media exhibit so-called transient chaos. So the chaos is there, but after some time the system comes at rest. And the lifetime of the chaotic transits increases exponentially with the system size. So larger systems have a longer lifetime of chaotic phases. And we also estimated the complexity of these chaotic dynamics in terms of the so-called Kaplan-York dimension based on the spectrum of Lyapunov exponents. And this increases also linearly with the system size and with the number of phase singularities, or phase singularities are actually the spiral tips here in this motion. Okay, so this is a little bit of excitable media dynamics, chaos, and so on. Now, if we want to study cardiac dynamics in a real heart, we have to measure something. So what can we measure? First of all, one can distinguish two cases. The first case is that we consider an isolated heart taken off the body and put into a perfusion system. And there you can use fluorescent dyes to measure the membrane potential, the calcium concentration on the surface of the heart. And this is called optical mapping. I will show you an example in a minute. You can also use several cameras, and then using different projections reconstruct the shape and the shape oscillations of the heart. And of course you could also put electrodes around the heart to measure the electric field, similar to an ECG. And finally you could use computer tomography scans to get detailed information about the geometry of the heart. And what we are currently doing, and which is quite promising, you could apply ultrasound measurements to get more information about the mechanical activity, the deformation, and the motion of the heart. Now, if you think about intact hearts which are inside the body, then, of course, you cannot apply these fluorescent dye measurements anymore. But you can still, of course, do electrical measurements of the surface of your body and solve the inverse problem. This is also called ECG imaging. It has a certain history of maybe 15 years now, mainly treated here as a static inverse problem, ill-posed problem with regularization methods and so on. You can do CT scans for the geometry, and finally, again, you can, of course, in this case also apply ultrasound measurements to learn more about the internal mechanical activity. So this is an example of the optical mapping approach, just to illustrate it. This is the heart. It's illuminated here with a green light, and then the fluorescent dye emits light in a different spectrum in red here, and the intensity is modulated by the voltage, or if you use a different dye, by the calcium concentration. But you see only what's going on the surface, of course. And here you see the setup. This is the heart. This is a perfusion system. This is illumination and different cameras. And if you use this approach, you have to cope with another problem, because at the end you want to separate the electrical waves and the mechanical motion. So these are the raw data, and since the heart is pumping, it's moving back and forth. So you have to do motion tracking using a correlation analysis of features on the surface. Then you get here now a new image where the motion is mainly reduced. And you see maybe here these shadows of black. If you now use image processing, you can amplify them, and then you see the electrical motion on the heart. This is one way. The other way is to add some pharmaceutical drugs which basically switch off the mechanical contraction. And this is shown here. This is an experiment with a pig heart in ventricular fibrillation. This is a ventricle. And you see here the chaotic pattern of the heart This is measured with many cameras so that we have a panoramic view on the dynamics. But this is only on the surface. So one of the topics we will see later is, of course, to get more insight about the internal dynamics. So much about the measurement modalities. Now a few words about the models we are at hand. So you can use very simple qualitative models like the Barclay model I've shown you before, or the Fitzhugh-Nagumo model. They have two variables. Then you can switch gears and use more advanced models, which are still quite qualitative with 3 or 8 variables. Or you can go to detailed ionic models like the neural models we heard about this morning, where you have 15, 27, or even more variables. If you are interested in this, you may have a look at the Scholarpedia article by Flavio Fenton and Elizabeth Sherry, who are discussing 45 different models on this page in detail. And the main structure of these models is the following. You have a differential equation for the membrane voltage, which is given by a diffusive term and by a sum of ion currents, which represent the different ion channels, sodium, potassium, and so on, or maybe also an injection current. These ion channels depend on gating variables and other variables, which are summarized here in this vector H. And this describes here the local cell dynamics, this set of differential equations. And as I said, you have, in the case of ionic models, 15 to 30 or even more variables, and 150 to 300 parameters in these models. And so this large number of parameters in particular could be a problem in a sense of overfitting, and that the models are maybe not so robust. We did a study with such a model, and we did a detailed bifurcation analysis, and we found that there are many parameters. If you change them just a little bit, they have a bifurcation in the model, and the dynamics is completely different. So this has to be considered carefully, I think. Okay. Now, if you have chosen your model, you can start to build up the full model. You take a CT of the geometry. You have a mesh, which is, of course, at the end a mesh which is deformable, and then you can also add fiber direction because the conductivity on the heart is different in different fiber directions. So you have a deformable reaction diffusion system. You choose your favorite model for the local cell dynamics, an ionic model, for example. Then you need also a model for the tissue dynamics. I will not go into the details there. Maybe it's just a mass spring model could be sufficient. And then you have a model for the heart, and you can start parameter estimation and model validation. Now, once you have a model, you want to apply it, and here's just a brief example of applications we have in mind. You can use this, of course, for novel diagnostic tools or for studying the impact of pharmaceutical interventions. We are interested in terminating ventricular fibrillation. Here is again the Pickard as an example. Well, in general, this is a serious topic because in Germany only we have 100 to 200,000 cardiac deaths per year due to ventricular fibrillation. And similar figures exist for Japan or the United States. And if this happens to you, you need immediate defibrillation because otherwise, as I said, you will die soon due to a lack of oxygen in your brain. And so the only therapy available currently is to apply a strong electric shock. And the idea is that you have, for example, here, this is the heart, these are these two paddles. You apply a very strong electric field which sets all the cardiac cells into the resting state. And then after the refractory period, they will be accessible again by the sine mode activity, so the normal heartbeat should start again. And this works, fortunately, but this is the case of an implantable device for those people who are in danger of getting this. They may get an implantable device. But the problem is the energy which is applied is pretty high, and therefore you have severe side effects like traumatic pain or also tissue damage. So therefore people are looking now for other methods to use less energy to achieve the same goal, to terminate the arrhythmia. And one important concept is the idea of so-called virtual electrodes. Premier and Krinsky discovered that if you put a heart in an electric field and you apply this field, then around so-called obstacles, which are basically blood vessels in the heart, scars, or fatty tissue, you have a hyperpolarization and a depolarization. And if this exceeds some threshold, then you can excite a wave from the obstacle. So here's a simple simulation indicating this phenomenon. We have here the field across the capacitor plates, and whenever we apply a field, we can induce here such a local wave which is emitted from this obstacle. So therefore it's called a virtual electrode. Now if you do this, here is an animation to illustrate the principle. You have a heart, you have several obstacles here, and you have spatial temporal chaos. And now in this movie we will switch on and off soon the fields, so you will see excitations here, and they can be used to terminate the electrical chaos here in this system. So now it should start at some point. Yeah, now it starts with a few pulses, and after these pulses are delivered, the whole dynamics is sent to a resting state. This works not only in a simulation in principle, but also in experimental work. This is a dog heart. These are again capacitor plates, electric field across, and whenever this turns red here, you will see a global electric field is applied, and after 5 pulses, with increasing synchronization in the tissue, as you can see, the chaotic activity is over. Okay, now we have the model. We can also simulate this in simulations. I can go over this quite quickly. In this case, these are CT data from a patient suffering from myocardial infarction. The myocardial infarction zone is here. You see now the electrical activity, which is now already chaotic here, and then we apply the pulses and send the system back to the normal heartbeat. So for these kind of simulations, we need, of course, reliable models and also possibilities to compare the simulation results with the scenarios which are taking place in the real heart. That's why we are interested to look inside the heart in a certain sense. Okay. So let me summarize at this point the tasks of data assimilation and parameter estimation. For the isolated hearts in the perfusion system, we want to reconstruct the intramural dynamics inside the heart from surface information which we get from fluorescent dye measurements. And we also may apply ultrasound imaging to get this information. And for intact hearts inside the body, which is a more difficult case, of course, you may try to reconstruct the dynamics of the heart using electrodes on the surface of your body. This is, again, has a long history, ECG imaging, but not with combined with dynamics. I think this is a new idea. And you can also then use mechanical information obtained from ultrasound imaging. And for doing all this, we need improved simulations, and at that point we need methods for parameter estimation and for model evaluation. So now let me, at the end of the talk, give you a few examples of what we did in the past to start this work. This is very preliminary, and I think there's a lot of things to do. So first we started with a simple synchronization-based method. So we have an experiment or a model which provides some signal here, and then we have a computer model, and we introduce here a coupling term, and we try to achieve synchronization between both of them, which is possible if the parameters P and Q are the same. And we applied this concept to the Buckley model, which describes the chaotic spiral wave dynamics. So you can see it here again. This was the local dynamics, the diffusion term, and then we have no flux boundary conditions. We implemented this on a GPU to speed up computations. And we considered a twin experiment where we have one system driving the others. The driving is implemented in the following way. We average over small areas. So these are sensor signals, and they are sent to the response system. And there the corresponding signal is created and used for coupling in a unidirectional way both systems. Now, if we start at time 0, the drive system may be already in a chaotic state. The response system has not started yet. Therefore, we see a big difference. But after some time, this system has already synchronized to the first system. The synchronization error is almost 0 already. Here is then we also studied, of course, the impact of measurement noise in these sensor signals that we generated, as you can see here. And we considered the parameter dependence. So there are basically two parameters, A and B, in the Berkeley model. And if we change the parameters of the response model, then we can here compute the error landscape of the synchronization error. And if we are here, then it's a unique minimum. That's the proper set of parameters. And here you see a movie. This is a driving system. This is a response system. After a short time, we have perfect synchronization because this model was using here the correct parameter values. If you use parameter values which are far off, you see here an increasing number of artifacts indicating bad synchronization, of course. And this works not only in a simulation. Here is a simple case of cardiac dynamics in a petri dish, a cell culture, where the electrical activity is again visualized using fluorescent dyes, and then the camera signal is sent to a simply Berkeley model. And as long as this error is visible here, there is a coupling in this direction. And so this system is now synchronizing with the experimental data. Now we switch off, and you can still see that it rotates with the same speed. So we have recovered basic features of this periodic dynamics. Now let me go to my last point, the estimability analysis of state variables. I want to motivate this with a simple example, which has nothing to do with cardiac dynamics, but maybe it's good for illustration purposes. We have here a three-dimensional chaotic circuit, electronic circuit, which produces a chaotic attractor. We take the first variable as our signal. We do a twin experiment. We use an optimization or 4D-VAR approach to estimate the three variables and the parameters P1, P2, P3, and P4. You can do this, and you see the result here. In green, you see this is time. This is the observed quantity. In green, you see the data, in this case without noise. You can do that with noise, but even without noise, you will see there's a problem. And the estimation result is a blue curve. It fits perfectly. So this is nice. And these are the other two variables which are reproduced by this process, and these are the parameters which are estimated. Now, since we did a twin experiment, we can compare them with the true results, and there is a big disappointment. You see the two variables are completely wrong, and also the parameter values are far off. The estimated values are much different from the true values, except for one parameter, P3, where everything is fine. So estimation works only for the observed variable and parameter P3. Everything else is wrong. This leads you to the question, why? And we studied several cases, and I think it's well known that the success in parameter and state estimation depends on the measured variable, the observable, which is available, and of course also on the particular variable or parameter you want to estimate. And the question is, which variables or parameters of a given model can be estimated from a given time series? And to answer this question, we want to employ the so-called delay coordinates map. So let's have a look at the discrete dynamical system, which generates this dynamics, and you can obtain a time series by observing the state with an observation function h, and then you can form the delay coordinates map in a d-dimensional space. So you map basically the original state space to a reconstruction state space by this map. And actually, we are interested in the opposite direction, because we want to use the observations which are here to get back to the original state, to estimate it. So we need the inverse delay coordinates map. And the question is it invertible, at least locally? And it is locally invertible at some point y here if the Jacobian matrix has a full rank. Or in other words, if its null space or kernel is zero-dimensional. And this is another illustration. This is our state space. This is a reconstruction space. And we have the linearized map. If we want to study small perturbations, we can use a singular value decomposition to express the pseudo-inverse and study its features. And this inverse map maps perturbations in the delay coordinate space back to the original state space. So if you have here a noisy signal, for example, then you know how this noise will affect the estimation of x. And you can quantify this by a quantity we call the uncertainty, which is given by this expression. And This is for the state vector only. You can include the parameter vector and consider the vector W of state and parameters, do the same delay coordinates map, and study its features. It maps perturbations of this space to observation space, and those perturbations which are in the null space of this map, of this Jacobi matrix, which have no impact on the observations, and that means they cannot be observed, or in other words, you cannot observe them from the measured data. So unfortunately, there is not enough time to go in all of the details, but I want to summarize maybe the main point is that we found out that the vanishing components of the basis vector of the null space indicate estimable parameters and also groups of redundant parameters, so that you know which parameter you have to fix to make the whole problem unique, to get a unique answer. And details about this can be found in this recent publication. So let me summarize. The heart is an excitable medium. It may exhibit spiral wave dynamics or even chaos, which is important from a medical point of view. We can measure its geometry using computer tomography. We can, on the surface, measure voltage, calcium dynamics, and also mechanics. But this is, of course, only possible with an isolated heart. We can use electrical sensors to learn more about the far field of the electrical pattern. And we can also use ultrasound to learn more about the mechanical motion inside the heart. And then we can use all these information and feed it into a mathematical model. The mathematical models basically consist of local cell dynamics plus a diffusion term. This is the electrical part. There is also electromechanical coupling, and therefore you need also a good mechanical model for the deformation of the heart. And when you have this, then you can do parameter estimation and model evaluation. And at the end, I've shown you very simple examples of synchronization-based approach and estimability concepts to address these questions. But there are, of course, many future problems to be solved. But I think it's a very promising field. And at this point, I would like to thank my co-workers, Stefan Luther, and our PhD students in our group for good collaboration and for providing figures, and our funding agencies, and finally you for your attention. Thank you very much.